Test, test.
We can hear you.
Now, okay, now I can hear you as well. Yeah. Hello, Crystal.
How are you?
Oh, doing good, thank you. Hello, Chamali.
Hi.
Tyler. Yeah, thanks for connecting ahead of time. Let's wait for everyone to connect. Hello, John. Hello, Ichi. Just for. Hello, Sophie. So please log in, connect to MATLAB, and open the script that I was sharing last time, the long one, to try to get through this as much as possible. And also make sure your email is open. I did send a link that we need to fill together to make a little practice of democracy to the best of our abilities. And also, you may just launch the script on the background as we speak, so that it goes through a little bit. Okay. 4 in class, 3 online, 2 is missing.
Is John in class, or I can text him?
Pardon me?
Is John there? I can text him if he's one of the ones missing.
Hello. John is here.
Okay. Well, you said turn's missing. I didn't. Oh, there you are. I didn't see you when he turned it.
So the first thing we are going to do. You can say hi, hello to the online part of the class. Yeah. So please consider to follow. If you just arrived, 2 things: open MATLAB and open script that I shared last time. And second, through the email, look at the link that I just sent to the room. So it is a Google Docs or whatever, Google Slides account, and we have 9 registered attendees of the class and 9 subjects. So we need to distribute talks between attendees to the maximal pleasure and minimal completes. How to do it? Just I see only one person is trying to look at this document. If you click on the link, it should bring you to collective editing of a document. So Yeah, so and I will fine touch after you make choices, but we'll do. But yeah, you can make first and second choice. So if I see your like affinity potential to do something different, I'll suggest and minimize damage. So yeah, and make second choices. Even if something, no. First three are super easy, and those who feel they understand everything try to feel from the bottom or in the middle. I just we all will try to practice democracy, but I will make sure that everything is populated and okay. So here, if you do not know how to fill, I click on the text box, click somewhere in the in here and type my name. And then I will move this text box to the subject that I want to present. So right away, yeah, thank you, John. This is also easy. Let me let me suggest again. You've pull it back if you don't like, but let me make suggestion for John and Crystal to take number 7 and number 8, which are the strongest. Oh, the hardest.
I'm gonna leave those for Pamela.
So, Crystal, would you feel comfortable trying? What do you like better, 7 or 8? I don't hear your microphone.
Do I get to ask you questions if I get stuck? Like, as I work on it?
Of course.
John, which one do you want actually, 7 or 8?
Okay, and John, I'm going to do something non-democratic. I'll move you to number 8.
John, did you prefer 7 or 8? I can do either.
I would prefer 7, but I can do 8.
Okay, I'll swap you.
All right, thank you, Crystal.
Okay, yeah, thank you. So, and please, I'll walk around seats if you have technical difficulties in putting your votes. But please try to feel. If there will be no votes, I can distribute tasks myself, but probably it will be better if there is a little flavor of your own wishes.
You want to choose 6? Isn't that letting you edit it?
That's the boxes.
Oh, you were a tiger.
I don't know. I have no idea.
You wanted 6?
No.
Fine.
No. Okay. Like you're moving.
Okay, sorry, I'll stop touching it. That's my bad.
No, I love this, but I can't move it. I can't type in anything. I'm like, which number I need to do.
Okay. So, which one? Can you type your name? Now let's just move to the subject where you want.
I have to choose the selected one or
Yeah, select whatever you like. Okay, excellent. Yeah, thank you. Yeah, thank you. Yeah, you can return, and now if you try to open it anyway, you'll see your. Which one? Yeah. Z at the end, right? Okay. So Faiz, Tyler, Timon, Chameli, Sohi, Payman, June, Crystal, Yuchi. Oh, we did everything, right? Do you see any no double booking and no empty spots? Okay, then I'll give a second glance when I meditate without in silence, but tentatively let's do this way. And for first three, it will be based on the previous two labs, right? So basically, Faiz, Tyler, and Sinyang, please teach us how to use MATLAB. And you can watch recordings from previous two labs, right? The goal, the reason for these things, since some of us were not using MATLAB every day, and even if we do some advanced things, we can forget some basic stuff, and you can remind us. For remaining 6 things, I will try my best to go over each of them this hour. And for basic ideas behind it, you have seen me trying to explain script by slides. So this is a backup. If if you're too busy, there is no time to prepare, you can at least tell approximately what your think is. But ideally, presentation should include demonstration, like screenshots of your personal attempt to run, and show like if there are failures or errors, also show it, because we can learn based on your failures. So it's nothing wrong if something doesn't work, and you can focus attention on the whole class. What are underwater stones? Okay. So screenshot, screen clipping. Just in case if something happens with online version, I have a copy of the choices by this meeting. Now let's open MATLAB, and I'll stop wherever it went through. Control-C. So I'll try to be what's going on? It's not expecting to recall these figures. So input parameters. The most important input parameter is J, which is coupling between near spins, and right now is set to negative value, which will be not quite correct for our problem, but it is a limiting case where the script is expected to work with less problems. This mu is gyromagnetic ratio, V magnetic field, and in the research stage after you do presentations, one may try a couple of values of magnetic field, but primarily one would third of a class will explore the same value, negative third with J equals 0, which will reproduce result that we put in class and in your homework, or it will be just collection of independent spins. And third of a class will explore by flipping this sign from minus to plus. So Boltzmann constant is well, temperature times Boltzmann constant is selected in terms of room temperature and the conversion factor. So whenever possible, one may try to use so-called atomic units in which mass of electron, charge of electron are equal one, and in these units, all equations, most of constants equal one, and equations become a little shorter. And this 27 factor is a factor of conversion for these atomic units, and 20 from electron volts to atomic units, and 27 is room temperature in electron volts. Bond between ruthenium atoms, but it is not quite needed. And I think whoever goes over the so this stuff about setting unit cells will go for the presenter focusing on subject 5, so he. And I will finish for CHEM and for input parameters. Another thing that we are not going to, likely we are not going to change, but there is a chance. So these parameters here, and they're used as variables later in the code. So if we look on number of unit cells, so we have 4 unit cells along one axis, 4 unit cells along another axis, so it's Ka, Kb, and number of nuclei is how many explicit atoms in one unit cell, first and second. And later on there will be cycle of them, and technically one can rerun the code for maybe smaller amount, and then it will be quicker and less precise. For bigger amount, then it will be incredibly long but more precise, and making them non-equal. And if one multiply all this, it is total number of atoms, atomic size. So the record where there are rectangular brackets and nothing inside, it is an attempt to declare variable for future use as a vector matrix. But at this point, when it is declared, it is empty. So we plan to have the list here, list of nuclei with increasing length. We will populate it, and the length of the vector will increase. So inside at each step, we add more and more atoms into this list. And last thing, last thing for the presenter number 4 is well, 2 last things. Scan of temperatures, so variable scan, and those things, if the code will be written by a professional programmer with elegant style of programming, those parameters will be in the specific input file at the beginning. Like right now it is inside in Y99, so it instructs to screen temperature in the range from 0 to 6 times of the room temperature. So room temperature is 300 Kelvin. 3 times is about 1,800. So if one needs to speed up the code for tests, one can put here only single number or shorten this last value can be put something small. So right now here is about around 100 points, which makes it so long. The parameters one can change the last temperature and the step instead of temperatures. And now I'm confident the very, very last thing for the input parameters is a place where we finished search of minimum and start subject 8, start loop over microstates. Yes, here, line 294. So in this place, it is another big number which makes the code to work excessively long. And we're not going to run the whole code right now as a demonstration. But if we need to speed it up, number of microstates, or I would find it by scrolling through, is set to 20,000. But if I set it like 10 or 100, it will be very imprecise, but it will work immediately. So, Chamele,
yeah.
Okay, I should, yeah, it's better if I share screen. Sorry, I didn't do it before. So, Chamele, do you have any questions? Is this enough and clear?
Oh, yeah.
Okay, yeah, thank you.
Not right now, yeah.
Okay.
Thank you.
I will try to rush to cover as much as possible. So, next, periodic boundaries and Ising Hamiltonian. Thank you, Sohi, for selecting it. It's the hardest things are 8, 7, and 5. So you are by selecting. Thank you for selecting hard topic. And by the way, this multiple figures did appear because I stopped the code in too early. And if I want to fix it at some point, I need to scroll for any place in the code that tells the word figure and put % in front of it. Or wait until the code is finished. Okay, so let's go back to the beginning. Okay, so if these few lines are clear, then the rest will be straightforward. But this couple of lines are really out of comfort zone for not only for non-scientific people, even in those who are dealing with STEM subjects, those are out of range. So first, as chemists, we typically focus on standalone mode when we do not need to think about periodic lines. It's more for physics. But even if we decide to open periodic lattices, it's much more comfortable to deal with rectangle, like chessboard, 90 degrees cells. But here, due to symmetry of this problem, the cell is non-rectangular. So annotation goes well. So the A axis go parallel to X, right? So it goes parallel to X. But B axis, this one, B, is at some, it's like 30 degrees here and 60 degrees here. So vector B is contributed from sine 30 degrees component times X. And in the Y direction, it is cosine 30. So to define this vector. So the unit vectors AA and B deviate from Cartesian coordinates. And if you go back to the matter, there are this line from 12 to 15. So along X, so it is two-dimensional vector. Along X, it is size of the unit in the cell, and along Y, it is 0. And for B, along X, it is 0.5, which is sine of 30 degrees. And along Y, it is square root 3/2, which is sine of 30 degrees. So it's vector of two components. Make sense? Okay. Now, positions of first and second atom. We need to set up coordinates of the first atom and second atom in terms of these atomic units. And this is minimizing the evil. One can do everything in Cartesian, but then equations will become longer and unit cell will become bigger. It will be less comfortable for final calculations. So one needs to suffer a little with this curvilinear coordinates, but then one is getting benefits. So approximately this, you see this yellow lines, right? So it is like tic-tac-toe 3x3 matrix, right? But here it is curvilinear or tilted. So the first atom is placed on the first intersection, second on the second intersection, but in this slanted coordinates. So for first atom, we have the 1/3 of A and plus 1/3 of B, right? So atom number 1. And atom number 2 is 2/3 of A and 2/3 of B. And since A and B are vectors, by practicing this operation, one will get their projection in Cartesian coordinates in case we need it. Let's go back to.
Where is that 1/3?
Also, so I understand the question. If one draws the honeycomb lattice and tries to identify minimal pattern that repeats, then the smallest thing will be of these two atoms. And if one does math trying to find coordinates, I'm not telling how to solve this problem. I'm just declaring the solution. Then the optimal, the best position will be having these atoms here, here and there, 1/3. So it having 1/3 and 2/3 for A and B, and then it will create a bond, and then the next, so the bond will be diagonal of this little diamond, right? If we replicate periodic cell, then there will be shorter subdiagonal of the same diamond, which will be of the double diamond. So it will be another chemical bond. So by doing math of this 1930 degrees diamonds, one will get that the bonds between neighbors are the same if one set these atoms in this position. And if one continues this line, there is a couple of empty diamonds here and there. So it is a void, like in the center of hexagonal, same as in benzene. So this trick will help to model the minimal unit cell of this honeycomb lattice. And when I saw it for the first time, it was throwing my mind off, because honeycomb, I expect to see 6 hexagonal, and here are only 2. One can do a bigger unit cell, and one can do a rectangular. If, for example, I cut the cell this way with 4 atoms, then it will repeat itself, this, and it will form honeycomb. Or I can do even bigger, but then it will be much larger number of atoms in unit. So we want to try to be minimalistic, because if as a limiting case, we may try to run this code only for 1 unit cell instead of 4x4. So it's minimalistic cell that reproduces properties of the whole system. Yes, this
one.
Yes.
Okay.
Okay. And then we have this atom 1 and atom 2. And now atom 1 and atom 2 are expressed in Cartesian. By the way, here I think it is my error. It should be 3. Yes.
Okay. Okay. That was my second point.
Yes. Yes. Thank you. Without talking and presenting, the code will be malignant. Yeah. Thank you for helping to fix it. Now, a little bit more in this subject, we need to, so this stuff on building list of nuclei is quite, well, I'm going to cover it. So we set up a cycle inside of 1 unit cell. So number of nuclei will be equal to. And then we compute number of this basis vectors. So coordinates of each atom based on whether it is first or second nuclei. And then after this step, we add this atom into list of nuclei. And then we repeat it for M and N is number of unit cells in this diamond structure. So if we go here and we type, just type nuke, maybe nuke apostrophe. So it will show positions of this like first atom, second atom, third atom in X and Y coordinates. And later on, there will be chance to visualize it, because for these abstract things, it's better to have something visualized to check if things are going in the right way.
Why is the second and third the same number? Or
second and third are the same? No.
Or
Their x projections are the same, but y projections are different. So each atom in this two-dimensional lattice is defined by two coordinates. I do not decline that I made some errors, but here there is no error. It's
well, no, I was just trying to figure out why or how or.
Huh?
Oh no, I just trying to figure out. So gotcha. So those are like that. Okay.
Let's look on the image and see what happens. So this is likely 1, this is likely 2, and this is likely 3. So 3 and 1 will have the same y coordinate, right? So several atoms will have the same y coordinate. And here in this, several atoms will have the same x coordinate. Okay? So coincidence is not coincidental. Thank you, Crystal. So continuing with this subject. And let's make a decision what we do if our time today expires and you still want to hear the end of the story. I think you all are very busy and your schedule doesn't allow to meet again. Probably I can just sit in empty room in front of computer and make a record brief presentation and share, right? If I decide to do it at a certain time, I will invite whoever wants to join, but I cannot count on your time because you are the busiest people on the universe. I know that you need to take classes, do research, and some of you are doing teaching assistantship. So you're carrying a triple role. So this NUC list of nuclei, and there is a long stuff that is not in, even if we extend time, I will not cover, but we create a list of neighbors, and let me show what it targets to get. So for each atom, one needs to identify who are neighbors of this atom. And one neighbor is natural because it is in the same unit cell, but we need to identify neighbors who are in another unit cell. Right? And when this identification of neighbors is done, so I'm making quite big jump forward. If needed, I'll return back and tell, but let's a little speed up. So if I write, for example, if I select 2 by 2 lattice, because otherwise if you do 2 by 2 unit cells, then this A11, B11 will be 2 atoms from the first unit cell, A12, B12 from the second, third, and fourth. And then I can arrange a table where this will correspond also to A11, B11. So same list of atoms. And now, after I identify all atomic size, all nuclei, the table shows pairs of atoms. So intersection, each cell in this table shows pair of atoms. And now in this list of pairs, I can tell whether certain pairs are neighbors or not neighbors. So you see that for each atom, there are 3 neighbors. And in each place where I identify a neighbor, I put coupling term J, because neighbors interact with their spins. Each time when atom meets itself, I put here gyromagnetic times magnetic field, because spin can be flipped by external magnetic field. And when atoms are not neighbors, I put 0, because not neighbors do not contribute to the energy. So the practical task for each to compose such table is to identify who are the neighbors. So for second atom, neighbors will be there, there, and there. And then for each atom, there is a list of neighbors. And this table, if it is set up correctly, is called Ising Hamiltonian, because we are not the first who set it up. And it shows us how to compose energy of the spin lattice if we know orientation of spin at each atomic site. So I would call it Ising Hamiltonian. Ising Hamiltonian. And for the sake of time, I'll try to identify in the code the place where this Ising Hamiltonian is set up. The way how to go from the lattice to identify neighbors and form this matrix is a little painful. So if you figure out or you consult with me, we can do it, but it will be too much for the class. Okay. Back to the code. So this things were like III. It is steps towards identifying the neighbor. And just a few seconds, and I'll tell what it is important. So it is a conversion from index of nuclei and index of unit cell towards unified index where we count all atoms 1, 2, 3, 4, 5. And after it is, yeah, by the way, this little command will show. Okay. So it shows this atomic sites, right? And in two-dimensional plane. So maybe, well, let's stop here and continue further. Now, this Ising Hamiltonian will be placed in this matrix. It will be number of atoms times number of atoms. And here is how it is populated. So it lists the atom number I, and then this III is the list of neighbors. So whoever are the neighbors for number first, second, and third neighbor for this atom are listed in this place. And if we have identified the neighbor, we add this letter J to this Hamiltonian. And this matrix called Ising will be later used to for all subsequent procedures. And the magnetization due to external field will be just added on the diagram. So by now we are finished subject 5. Okay. So thank you for selecting it. Send me any questions. And I think it is hard but doable. And please try to, all presenters, please try to squeeze your presentation into 5 minutes and dry run with stopwatch, because we need to respect time of everyone in the class, and you may have some other meetings. So if we 5 times 9 will be 45, and there will be questions, I'm sure. So then we'll add a little time, and we will be finished in maybe 1 hour and 10 minutes, something like that. If in previous years, well, I never taught this class, but I taught similar style, and every time someone in the class wants to brag with the knowledge and makes a presentation for 25 minutes. Please don't. Just tell me, I know so many things. Here are my slides, but I will stop here. I will give you credit. Just do not waste time of your partners. It's not a frivolous thing. It's the only way how we can organize. Okay, fabricate random microstates. Payman, are you online? Okay.
Yes.
Thank you. I'll try to cover your thing, and then maybe it. Well, please help me to watch the time. I do not want to override your time limits. So we'll definitely finish number 6, and then maybe for most important 7, 8, 9, I will need to make recordings at home and share. And thank you to heroes who agreed to do last 3 things. Okay, so fabricate random microstates. So again, if the author of the script will be a professional programmer, it will be done more elegantly. For example, some repeating patterns will be stored in different files and then called as subroutines. I do some foreman programming and just copy paste. For example, this fragment takes like about 3 times, but it is a common thing, and most well, scientifically not most important, but practically without the step analysis is possible. So we set up a vector called spin. The vector spin has size equal to number of atoms. So we need to populate this spin vector by either 1 or -1 or +1, +1/2, -1/2. And we cannot accept other values. It should be literally +1/2 or -1/2. And we want to make it run. Why? Because if the system exists at elevated temperature, in thermodynamics and statistical mechanics, one doesn't look for reasons. One just processes the consequences. So if by some reason the element of ensemble is random in a specific way, we need to have a way to process it. So at the end of the cycle, each value of spin vector, of spin variable, must be populated by either +1/2 or -1. And also, one can add magnetization plus the spin. So if we multiply total spin times gyromagnetic stuff, it will be magnetization of the cell. So if all number of spins up and spin down are 0, it will be 0 magnetization. If all are arranged in the same direction, it will be like ferromagnetic, right? So we add together. So at the beginning of the cycle, we set up spin equals -1/2. And if I comment out, if I delete next 4 lines, then it will set up all spins now. But it is not what we want to do. So there is a command RA and D we can try it in the command line. So it gives a random number between 0 and 1. And each time I execute it, it gives different number. Right? So it's throwing a dice or playing this cubes with from 1 to 6. It's a random number. And now, based on this random number, we need to assign whether it will be positive or negative. So we can subtract 1/2 and then check whether the result is bigger than 0 or smaller than 0. So if these random numbers are distributed evenly, homogeneously, then half of the outcomes will be plus, half will be minus. And then we have the construction if and. So if it was positive, we set up spin equals positive. So it overrides the value that we set up before, right? And by the end of the cycle, we have populated all spins in the microstate with certain values. And we also know the magnetization. So there should be a couple of lines in the code to visualize it. And if you will go over editing this, it would be healthier to put percent each time you see the word figure. Otherwise, you saw this error. I overlooked it. When I ran it just before the class, it generated like 300 figures, which is not healthy. If one removes this opening of new figures, this error will disappear. So here is a couple of commands to visualize the value. So we already saw this plotting the nuclear. Plotting nuclear will put little circles at the points in Cartesian points where there are atoms. Here I use plot 3 instead of plot to make sure that it is 3-dimensional because I want to use 3rd dimension for spins. And this little subroutine just checks the distance between nuclei as delta x squared plus delta y squared and then square root. And if this distance is less than 4, it draws a line. So if I run this from here to there, okay, go to command line. Paste. And hit enter. Then I just do not have energy to erase all these figures one by one. Next time I will avoid this error.
What does hold off and hold on do?
I will answer in a second. I'm excited with scrolling through figures, but I have clear mind and I have words. I just need to organize them in the best. So let's better open new figure. New figure. Hit here. Paste. So it, in addition to this points, it makes lines connecting them. So hold on and hold off. If you do not type hold on, then anytime you practice any graphical command like plot, line, and there are additional commands, it will override anything you did before. But if you want to draw several lines, or you want to add comments, or you want to accumulate graphic information, you type hold on. So I want to add together these points and lines and hold off just in case I forgot what I did before. I want to erase everything on this figure panel and start it over and then accumulate it across the cycle. So going forward. And here are a couple of commands that will draw stems. You draw little sticks out of each atom, positive or negative, depending up or down, depending on the value. So if I just copy paste this little thing, copy, paste here. So it shows several sticks upwards, several downwards. And it doesn't change the way how the code is working, but I think without this illustration, there is a big chance to make multiple errors. At least one can make double check that what we hypothetically imagine corresponds to what we practically model. And these little circles on the top are added to make it more visible, and red and blue also to increase the visibility. So Payman, if you present it, or if everyone in the class, if you do it as a part of research, you may illustrate microstates and make correlation between image like this and energy of a state. Right? This correlation will be very different for spin coupling parameters. For J negative, as it is set up now, J 0, which would correspond to result we got in class and in your homework, and J positive, which is most challenging thing. So it is J positive for the future, for your research will be likely most interesting and scientifically valuable, but it is also highest risk. So the code may fail to work because there are some objective difficulties I'll talk about. Okay, let's check if anything else is here for Payman. Fabricate microstates and visualize. Yeah, I think we are done. Payman, do you have any questions on this subject? Or it is more or less okay?
It's okay.
Okay, thank you. So how are we doing this time? Does anyone in the class has urgent appointments, or you are tired? So I'll try to start next thing, but probably so for the benefit of John, but for Crystal and Yuchi, no chance. I think we will need to stop, and I will do recordings at home. Thursday, likely tomorrow. Yes, Thursday is my third vacation of the week. Well, I'm joking. It's busy for work from home. And I'll do about maybe 20 minutes about subject 8 and 20 about 9. And when you look, practice and compress. So minimization, Metropolis, Monte Carlo. And by the way, this command is how to convert value of spins into energies. So you multiply Ising Hamiltonian by spin vector from the front and from the bottom, and at the bottom it should, in the front it should be rho, on the bottom it should be bone. And then it just one subtracts magnetization times magnetic field. And this line will be also repeated many times for each microstate. Okay, Metropolis. Yeah, this is additional comment to who is presenting. No, number 4, the initial variables.
Number 4, the parameters.
Chamele, yes.
Yeah, it's me.
Okay, yeah, thank you. So line 175, parameters, number of microstates. So if one wants, if one doesn't care about precision and wants to turn around quicker, go to line 175 and reduce this number to like maybe 1,000 or some smaller number.
Okay.
Okay, so the Metropolis algorithm starts with 227. This algorithm is widely used in statistical mechanics modeling of a lot of chemical processes, but originally it was designed for this Ising problem, and it is the best method for it. So you'll find in Wikipedia, on online search, some additional materials if you need. The idea is that one repeats throwing the dice several times. First time it is completely random, and then one tries to flip one spin and check whether it will increase or decrease the energy. So it will bring the system towards the minimum. So before this optimization starts, one all creates this distribution of spins, finds the energy, and then in the optimization loop, one is trying to minimize. So this algorithm should converge to a global minimum in number of steps equal to a number of spins. So it should be just K-mods. But I want, like, you know, if someone is confident, then you tell, I'm 200% sure, right? So here I am 12,800% sure. So I multiply minimal necessary number by a big number to be sure that whatever happens with any combination of random numbers, it definitely will come to a minimum, but it is a precaution. Now, what is this line? Copy. So this line is taking random number between 0 and 1, multiplies this by the number of atoms, and then takes integer out. And this -2 here and +1 there, it's just adjustment so that it will fail in the right range. And then by practicing this command again and again, see, in current settings of the code, total number of atoms is 32. By practicing this command, we get an integer, discrete random number between 1 and 32. So we see the numbers like 5, 21, 32. So it will be our trial atom. We will focus on atom number, whatever comes out of this index command. Then the value of a spin at this certain index is flipped. So the process we are describing here is a little bit artificial. So all other things and next two presenters about statistical average, statistical partition function and finding energy and heat capacity are very natural things. But this one is human, is an unnatural exploration of the system. So it's not typical way to flip certain spin in experiment, but we hypothetically consider what would happen if we can, with microscope and little manipulator, select specific spin and flip its value. So we flip the spin by this command. Then we compute magnetization of this microstate by adding together all spins. And then we compute energy of this microstate, but we call it candidate, because we do not know whether it will be good or bad to flip this certain spin. Okay? And then after we have found this candidate, we check whether it is bigger or smaller than the previously defined energy of a microstate, the energy of the original microstate. So if the energy of this candidate state is bigger, we want to flip spin back. So, oh, sorry, we do not want to do it. We flip it back. And then we recompute this magnetization of microstate based on the updated distribution of all states. So we just return back. If the energy of the candidate spin is favorable, it is smaller than our previous value, then we keep whatever we defined for magnetization of and spin distribution, and we just redefine. So now our current energy of the microstate that we believe is a minimum is set up to the candidate energy. And then we end optimization. Then we return back and try to flip another spin randomly. And by practicing this procedure long enough, it should bring the system to minimal energy. With guarantee, it works really well for negative value of the J factor. When we set J positive, it may fail for the there are potential challenges, because for J positive, there will be several local minima. There will be degeneracy of ground state. And right now, if we repeat this procedure for any value of magnetic field, any value of temperature, it again and again, it will come to the same ground state. In the future, we may come to challenging situations when one has the same parameters, repeat this procedure, and come to different ground states, which is not good. And what else? And there is a little thing which is already kind of a bridge to the next presentation. Basically, we are done for Metropolis. Here is a little thing that is, you can decide between presenter of subject 7 and 8. The thing belongs to both. So for the microstate, we compute the Boltzmann factor, which is energy of microstate divided by temperature. And then this Boltzmann factor can be used to computation of the update expectation value of energy, and which is our primary goal, and magnetization. So we take this energy of microstate times Boltzmann constant plus energy of the average energy of states computed before, where the proportions between those are dynamic. So if we would compute the list of microstate first and then add them together, we will just add we first compute Z MIP, which I believe is partition function. And then we will just add together energy of each microstate times its Boltzmann factor divided by the partition function. But since we have different lengths of this list, each new contribution has different proportion. The first contribution will be the only term, so it will be full. And when we go next to the list, this proportion changes and it will contribute less and less to overall sum. Any questions? Okay. So I probably can start number 8, but I believe it is not right thing in respect to your schedules. So please vote if I should start or should I stop. In class, can you show me one stop? Okay, two stops. Okay, it is equal to one indefinite, 2 against 2 to 4. I know that Crystal probably would be 4, but what's about Payment, Tyler, and CHEM759? Can you speak?
Okay.
What? Okay. So I will not cover the whole thing. I'll just point right places, and then we will depart in peace, because I know even if at least 1 or 2 people voted against, it means you need to be somewhere, and maybe you are just hesitant to declare it. So the core of the code, which is subject number 8, the screening of microstates starts in line 294. So the loop is the index of a microstate. It starts not from 1, but from 4, because there were some preliminary tests, including this finding the ground state with Metropolis. So 3 things: set random spins, compute under the word statistical sum. I imply the partition function. Observables and save observables. So the stuff for spin and magnetization is standard. Here, line 315 is energy of the microstate based on Ising Hamiltonian. And then the should be, yes. So Boltzmann factor plus previous value of the partition function will give the new updated version of the partition function. Right? And in line 342. And the line 333 is update of the expectation value of energy, which is our main goal. Okay. Now, the observables are saved in the variable ensemble, and later on it is saved. So this syntaxis means we add previous values of this matrix times, and then we add new column. So first, new row. First column is number of microstate. Second is energy of microstate. Third is magnetization of microstate. Fourth is Boltzmann factor. Fifth is updated value of partition function. And sixth is the expectation value of the energy. So this is an important thing, and others are less important. Okay. This part states, I will explain it in the online thing. So, and Yes. So the variable ensemble is saved into the file ensemble, and basically one can read it in other software like Origin or Excel, and plot the temperature as X and total energy as Y, which will be energy, what we did in class about 2 weeks ago, and then take derivative of Y over X and get the heat capacity. There are some additional features, there will be some additional tricks because this will be numerical data with fluctuations, so I need to make a spline. But basically, we are done at this point. Crystal, other general questions, non-technical about this unit? Are there any questions?
I have one for the end of class because I got an error because I know you said to try run the code and mine failed. I don't know why.
Okay, we'll fix it maybe in another session. I just wanted to finish because I feel some of you have other appointments. Yes.
I also got an error, but it still output all of the figures. If
all figures are outputted, it is. I'm not getting paid for being a good programmer. Sure. And sometimes it's it makes some errors for incompatible file, but it does the job. Right? I did several tests. So if it generates figures and if it saves the file called ensemble, then it is fine. It did its job.
Mine did not.
Okay.
I did something wrong.
Let's we need to continue. Maybe let's continue. Send me email about your schedule for Thursday, and anyone who needs help with the code, and I'll try to make out another additional Zoom meeting. So class is done. Everyone is welcome to disconnect or depart. I'll stay here to answer questions, but no new information. Sorry for taking more time. Go ahead with your other appointments. Whew. Oh, my pleasure. John, you're done with your question? Okay. Whew. What? Yes, I believe I did report, and as soon as we finish, it will start processing. And later, I will first watch it myself. If I told something wrong, I will chop it. Yes, trim it, and then place online. Okay. Anything? Any questions? I will try to answer now if they're immediate and easy, or postpone to special sessions if it is something longer.
Once everyone has their questions are done, can I ask you for why mine failed and what happened? Oh, you talk about their questions.
Other questions?
Yeah, like I said, once everyone gets their questions in for Camille, Tyler, payment, or whoever's there, can I ask why mine failed? Because mine failed.
Oh, yes, sure. And let me make you co-host if you are not yet. And then you can share screen. I'll check what is going on. And when we are done with just a second. When we are done with Monday presentations on next Wednesday, when we'll start next Wednesday.
Next Wednesday we didn't start.
No. The presentations are on Monday, right after the weekend. And I will need your slides on Sunday late night.
Right.
Yes. What's the problem? Graduate students are intellectual elite of the earth. It shouldn't be difficult. And the speed that you invest, that you do it so quick, will be also your credit. So I will not be critical in understanding all the circumstances. And after you do presentations, Crystal, just in a second. After you do presentations on Monday, we meet next Wednesday to start actual research projects. And I will visit with everyone to make sure that the codes are working. The code is working, so do not worry. For actual project, everyone will be able to run it, and I promise full help. Okay, so Crystal, can you please show your error message?
Yeah, because
No. Please, in the command line, it should when you type the code name in the command line, it gives the error messages.
Because I put this in and then I did the run to end.
Okay.
I
don't know.
Because I started at the beginning because I put my arrow up at the top, and then I clicked the run to end, and then it gave me this error.
Okay. And which one? Okay. So if your first error in this,
but it gave me no images.
So in the command line, can you please type who, WHO,
okay,
who space ensemble, this variable with uppercase, ensemble with uppercase, all uppercase.
All uppercase.
Enter. Try ensemble without who. Just the ensemble. Just a second. I will ensemble. Interesting. Type PWD. Type LS.
I'll list them. Okay.
And scroll to see that the code is.
Oh crap! That's my issue. I saved it on my desktop. Okay, I need to change my directory.
No, it should be fine. So
but I mean, I saved the file on my desktop. I'm in my folder right now. I need to get back up to my desktop.
But can you type name of the code right here? Maybe you already copied it here. Just RUCL3 or uppercase. R lowercase u CL3, and then hit the tab button. It should continue if it is there. Tabular, the button to the no. Yes.
Like I said, I have it on my desktop because I know where I saved it.
Okay, so you can either change directory here in the command line if you want to go to desktop, like CD once PWD.
Working directory and then
CD space double dot PWD
directory.
Once again, yeah. Now LS.
Yep, list on and
I think if now you type desktop CD space desktop, you will go where you need CD space desktop. Enter. Now type LS space. Try once again. LS space star.m. Star like .m. Enter. Okay. And now type the name of the code. Once again, UCL, and hit tab button. It should. And hit enter. So maybe with current settings, the code will work too long. It will expire your patience. But for tests, you can change the values of the variables for range of temperatures and for number of microstates, and then try running it once again. And then if it develops error, please show me what it types in the command line.
Okay.
By now, I think it is working. It goes quite far. So at least it did at least one scan of 20,000 microstates for a given temperature. And now it will go for about 600 different temperatures to accumulate this variable ensemble. But if there is no error by this point, it is a good sign.
Okay.
So I do not think you have a big issues, or I have a big. I don't think I have a big issue.
Yeah, I had it saved in the wrong spot. I knew because I knew it worked for you, and I knew it worked for John, and I knew it wasn't working for me, so I knew I did something wrong. I just wasn't sure what I messed up on, but I had it on the wrong file. So
it's a little. If you do not minimize parameters, if you run this settings that are there, it will run for like 20 minutes or half an hour or maybe a couple of hours, depending on how powerful your computer is. So each time it types KBT equals something, it goes to new temperature, and then you need to stopwatch this time and multiply by 600. So it will be like, if you do not change anything in the code, it will be done in half an hour.
Gotcha.
And common practice, common rule of thumb is to, for tests, use minimalistic parameters to avoid this waste of resources if you're not confident if things are working correctly. Any other questions?
Not right now. I'll have some by tomorrow once I start trying to figure out my piece.
Okay.
You says, was that what you did in class, everything you're saying on my part, or are you gonna still do some more on it tomorrow?
Pardon me?
The stuff you talked about in class, is that all you're gonna say on my part, or are you gonna do some more of it tomorrow?
No, I think I did cover. Maybe when we have only one thing left for heat capacities. And okay. I will, maybe I will do a little reminder of the things we discussed in the class, but basically you're ready to go.
Okay. Sounds good.
Okay.
Thank you.
So you authorize me to complete the session? Mm-hmm. Okay, thank you.
Thank you.
Yeah. Hey. Payman, any questions from your side?
No, I'm okay with it.
Okay, so then I suggest we fully complete the session and disconnect.
Okay, thank you.
Okay, thank you. Have a nice day.